Okay. Hello and welcome to today's edition of General Organic Lecture. Okay, we're going to pick up where we left off. Let me go back and share my screen. Okay, so when we left off, one of the things we were talking about was Lewis structures and formal charges. I went over this fairly quickly. We'll go into it in a little bit more detail. Chapter 1 of pushing electrons, when I assign that, teaches you the fundamentals of drawing Lewis structures. So backing up one here, these are the steps in drawing a Lewis structure. You determine the number of valence electrons, determine the arrangement of atoms. Okay, first you connect the atoms with single bonds, a single line, and then arrange the remaining electrons so that each atom has a complete valence shell, and then show bonding electrons as single lines, show non-bonding electrons as pairs of dots. Atoms will share one pair of electrons in a single bond, two pairs in a double bond, and three pairs in a triple bond. Okay, here are some examples of Lewis structures. Here are some with multiple bonds, double bonds and triple bonds. Okay, but these are some general rules that you'll get used to because most of what we're drawing, most of what we'll be working with, deals with just a few elements, okay, plus occasionally some others. Okay, remember that hydrogen can only form one bond. It has no unshared electrons. Carbon normally forms four bonds with no unshared electrons. Nitrogen forms three. Okay, think about ammonia, and it has one unshared pair. Oxygen has two bonds and two unshared pairs of electrons. A halogen will have one bond and three unshared pairs. If we go back to too far. HCl, okay, the halogen has one bond and it has three unshared pairs. Okay, formal charges. Okay, formal charges on an atom can be calculated using this formula. You take the group number, or the number of valence electrons. For carbon, that would be 4, nitrogen's 5, oxygen 6, halogen 7, for example. And then you subtract the unshared electrons, not the unshared pairs, but the unshared electrons. And then you also subtract the number of bonds, which is actually 1/2 of all shared electrons. Okay, so let's take a couple of examples from this list. Okay, taking a look at B. Here is carbon monoxide. And we can calculate the formal charges. For carbon, okay, it's group number 4, -2 unshared electrons, -3 bonds. So that's minus 1. Okay, we already know that carbon monoxide has no charge, and so by default, oxygen would have to be plus 1. Well, let's go ahead and calculate the formal charge on oxygen. Okay, so for oxygen, group 6, minus 2 for the unshared electrons, minus 3 for the number of bonds, and so that's plus 1. Okay, let's do letter E, which is the azide ion, and nitrogens are connected in this order. Right, so nitrogen has 5 electrons, there's 3 nitrogens, and then there's a minus charge. Okay, so that's 16 electrons. Okay, and if we count them up, 2, 4, 6, 8, 2, 4, 6, 8, that's 16 electrons. All right, nitrogen in the middle, okay, that's group 5 minus no unshared electrons minus 4 bonds. Okay, so that's plus 1. Nitrogen on the end. Okay, again, it's group 5, minus 4 for the unshared electrons, minus 2 for the number of bonds. That's minus 1. All right, so this nitrogen is minus, and then this one looks just like it, so that's also minus. And the individual formal charges have to add up to the overall charge. Right, BF4 minus. Boron is in the middle. Boron's in group 3, it's just before carbon. Okay, each fluorine has 7, so 7 times 4 is 28, plus 3 is 31, plus 1 for the minus charge, that's 32. Okay, if you count them up, there are 32 valence electrons. Okay, fluorine only forms 1 bond, so it has no charge. Boron is a group 3, so 3 minus 0 unshared electrons minus 4 bonds would be minus 1. Okay, again, here's carbon monoxide. Only one of these has the correct Lewis structure. Okay, we're looking for 2 things as far as identifying what is not a correct Lewis structure. One is, does the structure correspond to the correct number of valence electrons? Okay, so carbon has 4, oxygen has 6, so there should be 10 valence electrons. Okay, the other thing we want to look for is for second row elements, their valence shell cannot exceed 8 electrons. Okay, so right away in structure A, we have 2, 4, 6, 8, 10. Okay, so that's already a violation of the octet rule. So that's not a valid structure. Letter B is correct. Okay, we have 10 valence electrons and everyone has an octet. Okay, it turns out that C and D both have too many valence electrons. Okay, now we're going to look at another topic, and that's VSEPR, VSEPR. VSEPR stands for valence shell electron pair repulsion. And what this says is that electrons are localized into regions. And those electron-rich regions want to get as far apart as they can get. They repel each other, and so that will define the geometry of a particular molecule. Now, electron-rich regions include unshared pairs, single bonds, double bonds, triple bonds. Okay, if we have 4 electron-rich regions, okay, the best way for those to avoid each other is a tetrahedral geometry. And in a tetrahedral geometry, the bond angles are 109.5 degrees. Okay, a good example here is methane. In this drawing, the solid lines represent bonds in the plane of the screen. This wedge would be a hydrogen in front of the screen, and then this dash is a hydrogen behind the screen. If methane were planar, if it were flat, the bond angles would only be 90 degrees. Now, in the case of ammonia, tetrahedral refers to the electron pair geometry. We have 4 electron-rich regions. Now, the molecular geometry, which only includes the bonds, would be trigonal pyramidal. Nitrogen sits at the top of a 3-sided pyramid. Okay, and then over here we have water. Again, water has 4 electron-rich regions. The best way for these to avoid each other is a tetrahedral arrangement. And so that explains why water is bent and not linear. Okay, we have two bonds and 2 unshared pairs. Okay, if we have 3 electron-rich regions, then we have a trigonal planar arrangement with bond angles approximately 120 degrees. And some examples include ethylene and formaldehyde. Okay, the CH single bond is 1 electron-rich region. This is another. And then the carbon-carbon double bond is a 3rd electron-rich region. When you have 2 electron-rich regions, the ideal geometry is linear, okay, with bond angles of 180 degrees. Okay, while methane has 4 equivalent bonds and bond angles of 109.5, all the bond angles are the same. For ammonia, it turns out that this non-bonding pair takes up a lot of space. And so that compresses the HNH bond angle here. So you can see it's a little bit smaller. In the case of water, we have 2 unshared pairs, and these are more spread out, and so that's going to compress the HOH angle down to 104.5. Non-bonding pairs will take up more space than bonding pairs. Okay, so here we have some trigonal planar molecules. Okay, the approximate bond angles are 120. Okay, but since this bond is not the same as the other 2 bonds, okay, it turns out this one's a little bit less, this one's a little bit more, but they're close to 120. Okay, same way with ethylene. These are both planar molecules. Okay, all 4 atoms are in the same plane, all 6 atoms are in the same plane. So from a side view, we can see that this is a flat molecule. Okay, and then we have a couple examples of linear molecules, carbon dioxide and acetylene. Okay, let me do a couple examples here. Okay, we just had BF4 minus. Okay, so we would predict that that would be tetrahedral. Okay, another example would be, let's do G, CH3CHO. Okay, this carbon we would expect to be tetrahedral. Okay, 4 electron-rich groups. This carbon, though, would be trigonal planar. And the electron pairs around oxygen would also be trigonal planar. We've got 2 lone pairs, and then we've got this electron-rich group. All right, here's benzene. Okay, each carbon has 3 electron-rich groups. And so we would expect bond angles of about 120. In fact, benzene does have all 120-degree bond angles. And it has a flat geometry. Okay, next we'll look at polar and nonpolar molecules. Okay, last time we talked about polar and nonpolar bonds, which we could designate by differences in electronegativity. And in this example, carbon dioxide, the CO double bond is very polar. So this has polar bonds, but it is a nonpolar molecule. Okay, and that's because these 2 bond dipole moments oppose each other and they completely cancel each other out. This is the electron paramagnetic map. Electron density is greatest on the ends, and then it's electron lacking in the middle where it's blue. Okay, in the case of the water molecule, the 2 bond dipoles reinforce each other. Oxygen's more electronegative than hydrogen. And the overall bond dipole moment is in this direction. Okay, so we have an electron-rich region around the oxygen. We have an electron-sparse region around the hydrogens. Okay, we have a similar situation with nitrogen. Okay, because nitrogen's not a flat molecule, it is polar. Each NH bond is polarized toward the nitrogen, and the 3 bonds reinforce each other. Okay, some other examples. Here we have chloromethane. Chlorine is more electronegative than carbon. There's very little difference between carbon and hydrogen. Carbon is very slightly more electronegative than hydrogen. The difference is actually about 0.4. But this would be a polar molecule. Here's formaldehyde. Okay, basically the same situation. It's trigonal planar, but it's polar. And then acetylene has no net dipole moment, so it's nonpolar. Okay, next we're going to introduce the idea of resonance. Okay, here we have the carbonate ion, and there's 3 ways that we can draw this structure. Okay, notice the difference is the placement of the double bond. Turns out the actual structure is a composite of these 3. Okay, why do I say that? Okay, we can tell experimentally that a CO single bond is measurably longer than a CO double bond. carbonate ion does not have two long bonds and a short bond. Instead, all three bonds have exactly the same length. Okay, they're closer to that of a single bond than a double bond. The actual structure is a hybrid of these. These are called contributing structures. This was something that was described by Linus Pauling back in the 1930s. The contributing structures are separated by a double-headed arrow. Right, the double-headed arrow looks like this, okay, as opposed to this, which represents a reversible reaction or an equilibrium. These are two different things. In resonance structures, we are only moving around the electrons. Okay, here we can move atoms. Okay, so here we have the carbonate ion again. Here's the double-headed arrow. And this illustrates the pushing of electron pairs. Okay, so it's best to start at the negative charge. We push this pair of non-bonding electrons toward the carbon. That makes this a double bond. This carbon would have too many bonds though, so we push a pair of electrons up onto the oxygen. So this bonding pair now becomes a non-bonding pair on this oxygen. Okay, and then we, again, push electrons to form this third structure. Okay, we're going to be using curved arrows quite a bit in this course, and it's a symbol that's used to show the redistribution of valence electrons. Okay, there are only two allowed types of electron redistribution: from a bond to an adjacent atom, or from an atom to an adjacent bond. Okay, this is a very important skill, and you'll need to learn it well. Okay, we've alluded to some of this, but all acceptable contributing structures must have the same number of valence electrons. Okay, we can't gain or lose any. They have to obey the rules of covalent bonding. Hydrogen can only have one bond or two valence electrons, and no more than 8 electrons for second row elements: boron, carbon, nitrogen, oxygen, fluorine. Okay, third period elements can have up to 12. This would be like sulfur, phosphorus, arsenic, and some others. They can have up to 12. And they differ only in the distribution of valence electrons, and they have to have the same total number of paired and unpaired electrons. By unpaired, we mean odd single electrons. Okay, we've already done the carbonate ion. I'll go ahead and do the acetate ion. Okay, that looks like this. Okay, and it has an equivalent resonance structure. Okay, in which the single and doubly bonded oxygens trade places. Okay, so the negative charge is spread evenly between the two oxygens. Okay, here's nitrous oxide. Okay, the arrangement of atoms is NNO. Nitrous oxide, or laughing gas, is used in dental anesthesia. It's also a propellant in whip toppings. Okay, this structure is not valid. First of all, if we count the number of valence electrons around the central nitrogen, we've got 10. Again, that violates the octet rule. Nitrogen has a formal charge of -1. This one has a formal charge of +1. Okay, so this is the one of the resonance contributors for nitrous oxide. Okay, a good place to start is from the negative charge. Okay, you never push from a positive charge. Okay, so if we move a pair of electrons away from the negative charge, okay, then we get that invalid structure that's shown on the bottom. And so that means that we have to push a pair of electrons this way. Okay, since this non-bonding pair became a bonding pair, we now have a triple bond. And this bonding pair became a non-bonding pair. Okay, so that means there's a single bond to the oxygen. Okay. Nitrogen is still positive, has 4 bonds. The electrons move toward the oxygen, it's now negative. Okay, and again, we can prove that this has a negative formal charge. Oxygen is in group 6. Okay, -6 unshared electrons, -6 -1, which would be -1. Okay, and then we could also make an analogy to something like hydroxide ion that has just 1 bond to oxygen. Okay, so the actual structure of nitrous oxide is a composite of these two. Okay, so this NO bond has some double bond and some single bond character. This bond between the two nitrogens has some double bond and some triple bond character. Okay, so here we're changing topics again. Primarily in this course, we're going to be looking at s orbitals and p orbitals. S orbitals have a spherical shape. Okay, the 2s is larger in size than the 1s, and then the 3s is larger still, but they're all still spherical. P orbitals have a dumbbell or figure 8 shape. There's 3 p orbitals, and if we align them along the XYZ coordinate axes, okay, they are 90 degrees apart from each other. Right, when 2 hydrogen 1s atomic orbitals overlap, they form a bond, and we have the hydrogen molecule. Okay, I'm not going to go into too much detail about the derivation of hybrid orbitals, but if we look strictly at atomic orbitals and we look at certain molecules, okay, such as beryllium hydride, EH2. Okay, we know experimentally that beryllium hydride is linear. The electron configuration for beryllium is 1s2, 2s2. Okay, first of all, there's no unpaired electrons. If we were to excite one of those electrons, say into a 2p orbital, okay, now we've got two unpaired electrons that could be used to form bonds with hydrogen, but 1s overlap with a 2s would be significantly different than overlap with a 2p. Okay, they would be different energies, different lengths, different bond strengths, but it turns out they're both exactly the same. And it might not even be the right geometry. Okay, so hybridization involves mixing the mathematical functions that describe the three-dimensional shapes of s and p orbitals in such a way as to correspond with what we saw earlier with the Vesper shapes. Okay, the main thing that I want you to get from this is there's an association with shape, which corresponds to each one of these three types of orbitals. And SP, two SP atomic orbital, hybridized atomic orbitals, are in a linear arrangement. They're 180 degrees apart from each other. SP2 would be in a trigonal planar arrangement. SP3 would be in a tetrahedral. Okay, so this results from combining one s orbital with three p atomic orbitals. And when we do that, okay, we're going to take various linear combinations, and we end up with four sp3 hybrids. Okay, if we combine an s and two p's, we'll end up with three hybrid sp2 orbitals. Okay, and then we're going to look at different ways that bonds can be formed. We'll look at two ways, and these are direct head-on overlap and then parallel or side-to-side overlap. Okay, so here we have something like methane, which would have four sp3 orbitals in a tetrahedral arrangement. And each one of these could form a what's called a sigma bond with the hydrogen 1s. Okay, so here is the orbital picture for methane. Here it is for ammonia. Okay, the lone pair is also in an sp3 orbital, just not used for bonding. And then oxygen, again, has four of these sp3 hybrid orbitals, and it has two lone pairs. Okay, a single sp2 hybrid. Okay, sp2 is trigonal planar. Has two lobes of unequal size, and these are oriented 120 degrees apart from each other. Okay, we started out with three p orbitals, but we only used two of them for hybridization. That means we have one left over, and that's right here. Okay, so here are the three sp2 orbitals in a trigonal planar arrangement. Here is the unhybridized p orbital. Okay, so in ethylene we said was trigonal planar based on Vesper rules. Okay, the three sp2 orbitals form what we call sigma bonds. They're a direct overlap. And then this unhybridized p orbital overlaps side to side with another unhybridized p orbital, and that's called a pi bond. Pi bond overlaps in two places. So this is half of the pi bond, and then this is half of the pi bond below. Okay, so here is an sp hybridized. Okay, the two sp hybrids point in opposite directions, 180 degrees apart. And there are two of the 2p orbitals that are left over, and they're 90 degrees apart. Okay, so in something like acetylene, we have a sigma bond between the two carbons, between the two sp hybrid atomic orbitals, but then we have two pi bonds. Right, so an sp3 is tetrahedral. It involves 4 sigma bonds. sp2 involves 3 sigma bonds and 1 pi bond, okay, if there's a double bond involved. And sp corresponds to linear, okay? And a triple bond consists of 1 sigma and 2 pi bonds. Right, in the next lesson, we're going to look at something called functional groups. And functional groups are a set of atoms in a certain order that occur with great regularity. And knowing and understanding functional groups allows us to predict their chemical reactivity, and it also forms a basis for naming of organic compounds. Okay, so we'll go ahead and stop here. And I'm going to end the meeting.